Ches or TigerPhysics, and a couple of you have asked for some help in your AP Physics C homework problems, and so I have typed up the problems with the solutions and to lead you through them. The first problem you asked for was problem 33. An unfortunate person has had a broken leg that's been placed in traction. The patient's wearing a special boot with a pulley attached to the sole of the foot. The foot and the boot together have a mass of 4 kilograms, and the doctor decided to hang a 6 kilogram mass from the rope. The boot is held in suspense, is suspended by the ropes as shown in figure P6.33 that I've attached to the right of the problem, and the foot does not touch the bed. So you can see from the picture, you have a mass hanging vertically downwards on this string that goes around a couple of pulleys, and the pulleys are acting on the boot in a diagonal direction, one diagonal up and right and one diagonal down and right. They want you to do is determine the amount of tension in the ropes using Newton's laws to analyze the hanging masses. Then in the second part B, do the net traction force needed to pull the straight out on the leg, and what is the proper angle theta for the upper rope, and then what is the net traction force pulling on the leg. And they gave a hint that if the pulleys are frictionless, we'll assume the tension in the rope is constant from one end to the other end. And so we want to model this. Usually what we do is a particle model of things to simplify stuff. So we treat the foot as a single particle in equilibrium under the combined effects of a gravitational force, a tension force from the upper and lower sections of the traction rope, and an opposing traction force from the leg pulling back. We can also treat the hanging mass as a particle in equilibrium since it is not accelerating. Since the pulleys are frictionless, the tension will be treated to be the same everywhere in the rope. And because all the pulleys are in equilibrium, the net force is 0. So they don't contribute to the tension. The pulleys do not. So if you make a force diagram, the version the book had is they had the tension force for the hanging mass was upwards, and the force of gravity as shown in the force diagram here, the free body diagram, force of gravity is downwards, and then on the foot you've got a tension force diagonal up to the right and a tension force down to the right. You've got a gravitational force downwards on the foot. Notice it is smaller than the gravitational force in the hanging mass because the foot's 4 kilograms and the hanging mass is 6 kilograms, so the force of gravity on those two should be different. And then a traction force, since it's in equilibrium, everything should add up to a 0 net force. So to solve this, you're going to use a Newton's second law approach. We're going to take our force diagram we just made for the hanging mass. We'll write F equals ma, and then we'll substitute in for our net force, the tension force upwards minus the gravitational force downwards. That's going to be equal to m times a. Since it's not accelerating, I can replace m times a with a 0, and I get tension equals the force of gravity, mg, on the hanging mass. So they gave us 6 kilograms times acceleration due to gravity. In this case, we'll use 10 newtons per kilogram, the gravitational field strength, and we get 6 times 10. The kilograms cancel out, and we get a tension force of 60 newtons. In the book solution, they use 9.8 instead of 10. On the AP exam, they say use 10. Moving on, so that's part A. For part B, we'll again use Newton's second law for the vertical direction for the pulley attached to the foot. So we have F equals ma in the y direction, and we have the tension of the upper rope in the y component of it, minus the tension of the lower rope component in the y direction. And we have a force of gravity from the foot acting downwards, and those will be equal to m times a in the y direction. Again, not accelerating, so the m times a term is 0. So I can rearrange this and plug m times g in for force of gravity and add it over to the other side. I can replace the tension y component stuff with a force of tension times sine of the angle with them, because if we look at the picture, we can see that the angle drawn in the force diagram is measured from the horizontal axis, so the vertical component will be the opposite side when we resolve that vector for both of those tension forces. And that's also shown to us in the picture they've got there. So I've got force tension sine theta minus force tension sine 15 equals m mass of foot times the force of gravity g. And I want to solve for this angle, so I'm going to add over force tension sine 15 degrees over to the other side. And then I'm going to divide out the force of tension from the sine theta. So I get this equation here. Sine theta equals force tension sine of 15 degrees plus mass of foot times the gravitational acceleration. And that quantity is all divided by the force of tension. At this point, I've got everything on the side that I have numbers for and everything that I'm solving for on the other side of the equation. So I can plug those numbers in. 60 newtons times sine 15 degrees plus 4 kilograms times 10 newtons per kilogram. Divided all of that by 60 newtons. So when I plug those into my calculator, making sure I'm in degree mode, I get 15.5 newtons plus 40 newtons. Now, earlier tonight when I was doing this, I added these two up, and when I added them up, I had 65.5 newtons. And that's because I was thinking this was a 60 newtons initially, thinking it was the hanging mass and not the mass of the foot, to make that 40 newton force. And so I got 65.5 over 60, and that didn't seem to make sense because that would have given me a number larger than 1 to find the theta for. And when you do the inverse sine of a number larger than 1, your calculator gives you an error. So that was a pretty good clue. I had messed up. And so after checking things closer, I noticed that it should have been 40 newtons, not 60 here. And even 60 newtons times plus 15 shouldn't have given me 65. So I was just really tired and messed up pretty badly there. But I've fixed it since. So here you can see I have not fixed that on this part. I still have it as 65.5 when it should be 55.5 divided by 60. So if you do the inverse sine of that, you should get an angle around 67.7 degrees. And so that's our answer for that part. And it looks like from the picture that that angle is bigger than 15. So that should make sense that this is a bigger number than 15 because this upward force has to have the force of the foot's gravitational force and the downward pull of the y component of this tension force. Those two together have to equal this upward. So we need more of the tension force going upwards on the top half of that. So then we get to part C. Now it says use Newton's second law for the horizontal direction for the pulley attached to the foot. So we again do F equals ma from our force diagram. I've got 3 forces acting on the foot, the tension in the upper part in the x direction, and that's pulling to the right. And then I've got tension from the lower rope pulling to the right, also the x component, so those two get added together. And then the foot's pulling to the left, the traction force, so that's a minus, and that's equals m times a of the foot in the x direction, and that's a 0 because it's in equilibrium and not accelerating. So then I get this next equation, which just has the foot upper x and the foot lower x minus foot traction equals 0. And if I get that, so the foot traction is by itself, then I get the foot upper x and the foot upper lower together. That would be a cosine term since it's the x component of those forces. So foot traction is equal to ft cosine theta plus ft cosine 15 degrees. We just solved for the theta of 67.7 degrees. So I can plug in my tension force of 60 newtons times cosine of 67.7 degrees. Plug in my 60 newton tension force times cosine of 15. I get 22.8 newtons for the first term and 58 newtons for the second term. And so if I add those two together, and I think I'm doing the math correctly there, I get 80.8 newtons of foot traction on this foot. And that's the answer to part C of number 33. Hopefully that is making sense. On to number 35. For number 35, they said you've got a position of a 2 kilogram mass, which is given by x equals 2 times t to the third power minus 3 times t to the second power in meters. Looking at that where they say t is in seconds, those units don't seem like they would give you meters. So there's something, I think the problem here left off that 2 and 3's got to have some other units on it so that x becomes meters, but that's really not an important part of this problem, but the units should work out, and they don't appear to. And I don't know if I'm missing something or that's something else. But the question is, what is the net horizontal force on a mass at, for the first problem, part A of this is time 0 seconds, and what's going to be the net force in the horizontal direction if the time is 1 second. So as I've got written here, if we've got this situation where they give you an equation for position that is not one of those kinematic equations, kinematic mathematical models on your formula sheet, that is telling you that the constant acceleration equations do not apply here, so that you need to do some calculus to solve this problem. Since we're given a position equation with a time component in it, we could do a double derivative or a second derivative of our position and get the acceleration equation that applies for this problem. So if I'm starting with my position equation, I'm going to find my velocity, which based velocity with respect to time, or as a function of time, and that's going to be dx over dt. So that means I'm using the power rule. So I'm going to take this stuff here, and when I do dx over dt, that's going to give me units of meters per second. Again, the time units don't seem like they would work out for this, but I think that's a mistake in the book. So power rule, I'm going to take my power of 3, I'm going to subtract 1 from it, and I'm going to move that number that I had, 3, into the front as seen by the red lettering there. And then on my other part, I've got t squared, so I'm going to subtract 1 from that. I'm going to take my original number 2 and multiply it by the front. The numbers that are in front of the t's are constants, so they don't get changed by this. So I get 3 times 2, or 6, times t raised to the 3 minus 1 power, or the second power, minus 2 times 3 times t raised to the power of 2 minus 1, or 1. So that gives me my velocity equation. Then I use the power rule again to find acceleration. So I'm going to do dv dt. That's going to change my units into meters per second squared, because I'm basically dividing by another little chunk of time. I'm going to take this equation that I just found, 6t squared minus 6t to the first power. Usually we don't write the 1 there, but I have. And I'm going to do the power rule again. So I'm going to take that 2, that t squared is that power raised to, and I'm going to bring that in front. So I'm going to get 2 times 6, and then I'm going to take my power 2 minus 1, and that will give me that chunk of that equation. And then I'm going to get minus t1 to t raised to the first power minus 1, bring out that 1 that I originally had into the front. And so that gives me 12 times t to the first power minus 6 times t to the 0 power. And t to the first power can just be written as t, so 12t, and t to the 0 power is 1, so I can just write it as 6. I don't need the t there. So now I have an acceleration equation. Now that I have an acceleration equation, I can use F equals ma. So net force equals m times a. I have an equation for a that I replace it with. So I plug in the thing I just found, 12t minus 6s, plug that in. I've got a mass that was given to me at the start, which was 2 kilograms. So I'm going to take 2 kilograms times the quantity 12 times 0 seconds, since part A said solve at 0 seconds, minus 6. So I end up with 2 times minus 6, which gives me a magnitude of negative 12, or 12 for the magnitude, but negative for the direction. And the units would be kilogram times meter per second squared, and since it's a force, that should be written as a newton. So negative 12 newtons. For part B, it said do this at 1 second. So I do the exact same equation, but now I plug in 1 second where I had 0 seconds before. And, whoops, sorry about that. And I'm going to do 2 times 12, the quantity 12 times 1 minus 6. So I get 2 times 12 minus 6, or 6, positive. So I get 2 times positive 6. That gives me a positive 12. So in between 0 seconds and 1 second, this force changed directions. The net force changed directions. And so those are my 2 answers to 35. And we're in the home stretch now. As you can see, I got tired of typing. So I just went with a picture from the book. 55 you have a 1 kilogram block pressed against a vertical wood wall so a 1 kilogram wood block, and it's pressed by a 12 Newton force as shown in figure P6.55, which is pictured below. If the block is initially at rest, will it move upwards, move downwards, or stay at rest? So this question's a little trickier. As you can see by the little 2 bars there, that means that's a higher level problem. So we got to do a couple of things for this. So I'm going to solve stuff in the x direction. So I'm going to say F net equals, in the x direction equals m times a in the x direction. I've got a normal force. In this case, normal force is horizontal because the surface is vertical. So the normal force is to the right out of the wall. And then I've got the x component of my applied hand force on the block. And it's not accelerating, so then I've got 0 newtons for m times a. So that means my normal force is equal to the x component of my applied hand force, which would be the applied hand force times cosine of the angle theta. Because based on the picture, the angle is with the horizontal, so the x component would be a cosine term. So 12 newtons times cosine of 30 gives me 10.4 newtons. So my normal force is 10.4 newtons. And since we want to know friction, we need a normal force, most likely, to help us solve for friction. So then I have to switch what I'm looking at to the y direction, and I'm going to find the net force from just the applied force and force of gravity, so I know how much missing force is there to figure out how big a frictional force would be present to keep this block from accelerating. So I'm doing force applied in the y direction minus force of gravity. So I have force applied in the y direction is composed of the force applied of the hand on the block times sine of the theta minus mg. So I get 12 newtons times sine of 30. If your calculation in degree mode, that should be 6. And then I have 1 times 10 for 1 kilogram times 10 newtons per kilogram. Gives me a total of 10 newtons for my gravitational force. So I have 6 minus 10 gives me a minus 4 newtons. So that means that I would have to have a positive 4 newtons of friction to keep the block at rest. So since I have a downward force of 4 newtons here, the block would be accelerating if not for friction of 4 newtons. So now we got to go back and look at what is the max force friction can apply. And that is found by taking that inequality on your formula sheet. F friction is less than or equal to mu times normal force. Change it into an equality because we're at the maximum amount of static friction. So I'm going to also then have to look in my book for the wood-on-wood frictional coefficient of friction. And I should probably have that written in there. So that's something you look up in your book on a test. That would be given to you, that number. But that's a number we can look up. So normal force is from before the applied force on the block times cosine of the angle. So my friction max is equal to mu times the applied force of the hand on the block times cosine of the angle between them. So the number for a wood surface coefficient of friction on another wood surface is 0.5. So 0.5 times 12 newtons times cosine of 30 degrees. And you get the max force is going to be 0.5 times 10.4 newtons, the answer we got earlier. So that's going to give me 5.2 newtons for the max force. So since the static friction required to keep the block at rest is 4 newtons, which is less than the max amount that can be provided, the block's going to remain at rest. So hopefully that is helpful for telling you how to solve those problems, and most of it was clear. This has been Ches or Tiger Physics, and Lauren. I think we can both agree while Jessica is punny, there is no chance she's as punny as I am. All right, that's all for Tiger Physics. It's 9:11 right now, so it's time.